Hello and welcome to part 3 of lecture 18, where we're going to talk about the last topic covered in chapter 24, and that is the topic of polarization. Okay, so polarization of light is all about its directionality. Okay, but in a direction in a sense that we have not really thought about so far. We want to understand that unpolarized light is composed of many electromagnetic field vectors that all point perpendicular to the velocity of the wave, but in many directions within that perpendicular plane. And we want to learn that the three most common ways that light is polarized is through partial absorption, through a filter, reflection, and scattering. Okay, so we got absorptive, reflective, and scattering based polarization. Okay, and that's the kind of having a certain directionality. So, unpolarized light. Well, unpolarized light would be shown like in the picture. Okay, so if we look at the caption here, it says the red dot signifies the velocity vectors for a wave that are coming out of the page. Okay? So if the velocity of light is in the z direction, then the magnetic field and its associative amplitude, right? Remember the way that we've drawn light as a perpendicular wave of electric energy, and then a perpendicular wave of magnetic, basically not energy but field, right? Which is a representation of energy over distance, but specifically the field. So velocity of light is in the z direction. The magnetic field, I'm going to say electric field, lies in the x, y plane. Okay? If the E field in this plane points in many directions, then we call the light unpolarized. It's not directed. Okay. So the light is unpolarized. Now we're going to see there are ways to polarize that light. There are ways to give that light a particular defined direction, so it only points in one direction. So polarized light only has E field in one direction. For example, the y direction. Now it's got to be either y or x or some line between y and x, because it can't be the z direction if we're defining the velocity in the z direction, because the electric field would never be parallel to the velocity. Right. And I chose y direction kind of based on the picture here, right? Because we can imagine that being the y-axis. Now we can add some kind of 3D axes to this, something like this, right? So this is, I'll have you do it here. So this would be the z direction, the y direction, and the x direction. And z is coming out of the page. Okay? All right, so that's the idea, right? Now, the way we were going to polarize light, the ways we're going to talk about, they're all kind of based on this idea that somehow the other directions get absorbed. That energy gets turned into heat, gets turned into kinetic energy of some molecules, for example, and so it goes away, okay? And so that energy is no longer housed in the photon, right, in the light particle, or the light wave for that matter, if we're thinking light as a wave, which we are. You can kind of think of an analogy if you're whipping a string around in all directions, kind of wildly swinging it around. You would see a bunch of waves being transmitted down that string, and they'd be going in all different directions. But if there was some sort of slit that restricted the string to only be able to move up and down, then all of the wild directions of string amplitudes that hit the side of the slit would just get absorbed by friction, right? And so just kind of turn into heat. But then you'd have one direction that would survive, that would actually pass through your narrow opening, okay? So that's certainly the idea of partially absorptive polarization, which is the most common. And let's get to that, okay? So here are three types of polarization. We've got the absorptive, the reflective, and the scattering. Okay. The only two that we're going to handle numerically are absorptive and reflective. And absorptive again is the most common, most likely that you would see a problem based on absorptive polarization. Okay. So what is it? So partially or absorptive polarization is light. Only one direction of the electric field is able to pass through some sort of filter. So this is polarization, where only one direction of a electric field is able / allowed to pass through a filter. So what would that filter look like? Well, if you zoomed in on the microscopic level, the filter would probably look like a lot of narrow slits of some sort. Maybe it's kind of like bands of opacity, something that isn't very that's not going to transmit the light very well, and then bands of some transparent material, at least partially transparent. Okay, so that's the idea. And if we look at the picture, we could see that then we can think of this glass as our filter. In this case, this glass is made in such a way that it only has a vertical transmission axis. So it only allows electric fields to pass through that point in that direction. And so then the unpolarized light, after passing through this filter and its particular transmission axis, has an electric field that only points parallel to the transmission axis. Makes sense, right? That's the only part of the electric field that survived. The rest of the electric field and its associated energy just got absorbed into the filter, so the filter would have to heat up. Okay? We're not concerned about exactly how much it does, but that's conservation of energy. Now, interestingly, if we then had a second polarization filter, right, a second filter, and it was tilted a little bit, well, then some of the field would still survive, right? Because we'd have this electric field, and when it passed through this secondary filter, it would have some component that was parallel to that new filter, right? And so if you look at it, it says the analyzer allows the component of the light parallel to its axis to pass through. Okay, so we treat this as the hypotenuse, and then we just have some triangle, okay? And we have some smaller component that would be parallel to that new axis. So we can continue to have less light, because notice the amplitude gets smaller, right? We can continue to have less light pass through with these tilted transmission axes, all right? But some light will still pass through because there is still a component that is parallel, right? Now, if I had a polarization axis that was exactly at 90 degrees to the original polarization axis, then there wouldn't be a component that's parallel, and zero light would pass through, all right? But that secondary filter is often called the analyzer, okay? So two filters, okay, those are absorptive filters, used together are called an analyzer. So the first one is called the analyzer, and the polarizer. First one is called the polarizer, and the second one is called the analyzer. Those are just the names given to them. They're both filters. They both work on the property of absorptive polarization, but they're commonly called the polarizer and the analyzer, which I know is kind of a bit of a misnomer, right? The naming is strange. I always find it strange, but those are the names given to them, and we'll use them. Okay, so filter, polarizer, analyzer, these are all interchangeable terms, but when you have a combo of them, call them a polarizer and an analyzer. Okay, so we're going to see some formulas to work with that, some general properties. Okay, one big one, I'll repeat this in just a minute, is that when unpolarized light passes through that first polarizer, the energy that passes through, the amplitude, or the amount of energy that passes through is always going to be 1/2 the original unpolarized light. So we always have a intensity. That's the word I was looking for. So the intensity decreases by a factor of 1/2 when you go from unpolarized to any polarization. Okay, it could be horizontal, right? It happens to be drawn vertical in the picture, and so that's an important thing to remember. And subsequent losses of intensity are dependent on what is the comparative angle between them. Okay, but I'll mention this with the formulas. Let's get on with the terms. Okay, so the next type of polarization is reflective polarization. Okay, and so this is polarization. Okay, where certain angles of reflection transforms unpolarized light into polarized light. Okay, and there would be, you could have partial polarization, but we care about full polarization. And so unpolarized light becomes polarized along a single axis, right? So that would be kind of fully polarized because now there's just one direction left, single axis, if the angle between the reflected ray and the refracted ray is 90 degrees, which is pretty neat. So that's a condition we never talked about, right? We've talked a lot about the law of reflection, the law of refraction. We've talked about, what happens when the refracted ray is 90 degrees relative to normal. Well, that's total internal reflection, okay? But we've never really thought about the angle between the reflected ray and the refracted ray, okay? Well, now we are going to for the first time, and it's just really one special case. Okay, put it on a single axis. If angle between refracted ray, I'll draw a picture of this below, and reflected ray is 90 degrees. Okay. All right, last type, qualitative discussion about scattering polarization. Okay. So this is polarization caused by light interacting with molecules in a gas. Okay. All right, so ultimately scattering polarization has two approaches that can be taken to understanding it. The approach that we're taking is the wave property approach. This is treating light as a wave. That's really where we're at content-wise. We will talk more about light as a particle when we talk about Einstein's famous experiment that proved that light is a particle, but didn't disprove that light is a wave because those physical proofs remain, right? So light is both a wave and a particle. In general, you can think of light as a wave when it's passing through a transparent medium, like air or glass or something. And then you can think of it as a particle when it's directly interacting with another particle. And so then that kind of begs the question, well, scattering sounds like it's interacting with a particle. A molecule certainly seems to be a term that would be synonymous with particle. And so in some sense, the best understanding of scattering polarization is through the photon model of light, and to really think of it as a momentum based physical phenomenon. Now, we're not there yet. I'm not going to be talking about that in any meaningful way. But the interesting thing is that thinking of it as a wave actually does work quite well, all right? And so I would just kind of caution us to think of this as being one particular case where light interacting with matter is well explained through wave optics, okay, through physical optics, but that not being something that you should really rely on, and you should kind of have it in the back of your mind that if light is interacting with matter, then we should be thinking of it as a particle. Now, content-wise in the course, we're not there yet, so don't worry about it, but just kind of as a good rule of thumb, right? So, but with that caveat out of the way, we can go ahead and proceed with the picture, which is a really neat one, okay? So looking at this figure, what's going on is we kind of got the answer to two of children's favorite questions, and that's why is the sky blue and why are sunsets red, okay? It's kind of amazing, right, that you can explain it in just kind of one figure. I think that's amazing. So what's going on, right? Well, we've got incident light from the sun, which is unpolarized, right? And that's an important thing. That's going to be true in all of our cases. So if we want to kind of have a go-to unpolarized light, it's sunlight. All right. So looking up at the sky, in the direction of the sky where the sun is located, we got unpolarized light. All right. So what's going on then? Well, someone underneath, right, laying down, is going to look up and see the sky is blue. Why? Well, right here. The electric charges in the air molecules oscillate in the direction of the electric field of the incident light from the sun, acting as antennas that produce scattered light. The scattered light then reaches the observer directly below and is polarized in the z direction. Okay? So the molecules are going to be vibrating, okay? They're going to oscillate in the direction of the electric field, all right? And the electric, so that's the unpolarized light has electric fields in all directions, but we're going to have an oscillation that is only going to produce itself a new form of light, because it is then acting as an antenna. Those oscillating, all those electrons, all those accelerating electrons in the molecules in the air, well, all of them are based on the laws of electromagnetic induction. An accelerating electron creates a changing magnetic field. The changing magnetic field creates a changing electric field, and light is produced. Okay, so they're acting like antennas, and they're producing light. The type of light they produce is blue, and that light is transmitted perpendicular to the velocity of the original light from the sun. In other words, straight down. Okay? And the air molecules scatter blue light more effectively than red light. Okay? So that's just because of their particular properties. They oscillate. You can think of it, they have a resonant frequency that matches blue visible light. Okay? And it's not all molecules. It's just particular, I believe it's nitrogen. Okay? So it's nitrogen happens to have that particular resonant frequency. All right? So, okay, that kind of makes sense, right? So they're resonating, they're vibrating, they're acting like little antennas, and unlike an antenna, like a man-made antenna, like with a wire that creates an FM, radio wave or something, these antennas are molecular, right? They're much faster, and they're actually creating visible light, right? There's not man-made antennas, as far as I know, that create visible light. It's just too fast. It's too difficult to do. But on the molecular level, you can do it. Okay, so there we go. Then what's happening with the sunset? Well, if we think about it, then someone that's standing over here, direct line of sight with the sun, right? When that's going to happen when the sun is low in the sky, sunset. Well, they're going to observe reddened sunlight, because all the blue light, okay, was absorbed because it matched the resonant frequency of the molecules, and so all that's left is everything that's not blue, which is going to, when you overlay all the colors of the rainbow, tend towards red. All right? Okay. So simultaneously, we got why is the sky blue, why are sunsets red, all about scattering, all about air molecules acting as antennas, transmitting light, okay? Transmitting energy away of a particular frequency, okay? Okay, let's get down to our formulas, right? Not too many formulas, pretty good. All right, so our first formula is going to be the one for absorptive scattering, all right? And so this I represents intensity. So when we talk about absorptive scattering, we're going to be always doing it in the context of intensity, like how intense was the light, how much light passes through a particular polarizer. All right, so phi here represents the angle between the polarization axis of the analyzer and the polarization axis of the polarizer. Okay, so this is the angle, and I'll put the polarizer first. Angle between polarizer axis and analyzer axis. Okay, so it's the angle between those two axes. Okay, but we have to also remember that the first polarizer removes 1/2 intensity. So I'll put note that I equals 1/2 I naught, where I naught, and then here we'll have, here, I'll write this differently. You'll see why. So note I max equals 1/2 I naught, where I naught is intensity of the unpolarized light. You might be like, wait, maximum should be bigger than I naught, right? You're saying that I naught is twice max? Well, yeah, because max is just the intensity that came out of the polarizer. Okay, so this is just that's the intensity that left the polarizer, and this is the intensity that is leaving the analyzer. Okay? All right? So hopefully that makes sense. We'll see it in practice in just a minute. And then this next one is called Brewster's Law. Okay? And Brewster's law, based on Snell's law, is the one that says that there's that particular, based on the idea that if the angle between the reflected axis and the refracted axis is 90 degrees, then you get full polarization. And what that would look like is something like this. So let's draw a transition between two different substances. So something like that. All right. And we'll have our N1 and our N2. Okay, or A and B. So NA and NB. All right. If NA is air, then we'd just be dividing by 1, right? And so essentially we just a tangent of theta P. Okay, well, what is theta P? Let's draw our normal axes. Okay, make those dotted like this. All right, and then we'll have our reflected axis coming up. All right, so here we have our incident ray. We're going to have refraction. Right, the light is going to bend towards the normal because NB is going to be larger than NA. Okay, and then we're going to have our reflection like this. So then we have our angles. So this is our theta 1. This is going to be our theta B. All right, and then this angle here is just going to be equal to theta 1. Okay, and so then if this right here is 90, then we've achieved the condition that meets the criteria for Brewster's law. All right, we have, in that case, theta 1 equals theta P. All right, so I'll say down here, if angle between refracted ray and reflected ray is 90 degrees as shown, then theta 1, that's the incident angle, equals the Brewster angle, theta P. All right, and that's the angle that we wanted in order to get full polarization. Because in that case, the light that would be coming in would look like this. Okay, it would look like this unpolarized light. That'd be right there. Okay, and the light that would come out would just be on a single axis, and it is a specific axis. It's going to be polarized in the plane of the interface, and so the polarization would be, if we think of this like substance going into the board, the polarization would be along that plane. Okay, and so, but it'd be sort of like horizontal polarization. Right? If this is like a horizontal surface, like such as water or something. Okay? All right. Hopefully all makes sense. Let's do some examples. Okay, so first example, we're going to look at some polarization sheets. All right, so these are just absorptive polarizers. So 3 polarizing sheets are placed in a stack with the polarizer directions of the first and third perpendicular to each other. And what is the intensity of the light emerging from the third polarizer if the middle polarizer has a polarization direction that is 70 degrees to the first? Okay? All right, so what does this look like? So we just have 3 discs that are our polarizers / filters. Okay, so here's our first one, our second one, and our third one. All right, and then we have the light coming in. Right, so that's just the direction of the light. And then let's think about our axes. Okay, so the first and the third are perpendicular to each other, and so I'll make the first one vertical and I'll make the last one horizontal. And so this one will be our first polarization axis. Our last polarization axis is going to be like that. Okay, and then the middle one is 70 degrees. If the middle polarizer has a polarization direction that is 70 degrees to the first, okay, so 70 degrees to the first would be something like this. All right, and that's because this angle right here then would represent 70 degrees. So this angle there is 70 degrees. Okay? All right, and then so first of all, we have the unpolarized light come in and it's going to get polarized. So the first step, I'm going to kind of talk about our intensities. So I'll draw our intensities at the different stages. So this is the intensity of the light before it does anything. This will be the intensity of light after the first polarizer. This is the intensity of light after the second polarizer, and this is the intensity of light when it leaves the third polarizing sheet. Okay? And let's put this one down below so it's not crowded in there. Okay? All right, so then how do we tackle that? Well, we're going to, first of all, just use the rule to find the intensity of 1 compared to 2. Okay? So I1, that's the leaving the light, leaving the first vertical polarizer, would equal 1/2 of I naught. Okay? All right, and so our final answer is just going to be some fraction of I naught. Okay, so that's our first step. Okay, and then we need to find how much light is I2. What's the intensity of I2? Okay, and again, intensity is watts per square meter. Okay, so it's power per area. All right, so note, I'm making it, because I think it's easy to forget the units of intensity. So intensity is watts per square meter. Right, so it's joules per second per area. Energy per time per area. Right, that's intensity. All right. So I2 is going to, and I'm just going to use this formula right here. Okay. I max is going to be what left the first polarizer, and it's going to be cosine squared of phi. Okay, so I2 is then going to equal I1 times cosine squared of phi. Okay, well, that's going to be 1/2 I naught times cosine squared of 70 degrees. Okay, so then I2 is going to equal, let's see. All right, so get my calculator here. I'm just going to do cosine squared of 70 degrees. So cosine of 70 squared, make sure I'm in degree mode. Okay, so that's about 1/10. All right, and so then I'd multiply that by 0.5. All right, I'm going to get 0.05. Okay, so I get 0.058. Okay, working with 2 sig figs, and that's times I naught. Okay, and that's just because cosine squared of 70 gave me 0.11 or 12. Okay, and then take half of that. So essentially, so this effect here is giving me about 10% of the original intensity, but I already lost a half because I went from unpolarized to polarized. And so now relative to the unpolarized sunlight, if you will, I've got about 5% of the energy left. Okay, well, energy per time per area left. Okay, but that's not all. There's one last step. We need to find I3. Okay, and so I3, we're just going to do it again. Okay, so that's just going to be I2, because that's the intensity is going into that final polarizer. And what's the angle in this case? Well, it's 20 degrees. Okay, so it's going to be cosine squared of 20 degrees. Why 20 degrees? Because that's the angle between this polarizer and the next one. Okay, so it's always the angle between them. Okay, and obviously 90 minus 70 gives you 20, and we know it's got to be 90 minus 70 because these two polarizers, the first and the third, are perpendicular to each other. All right. So then I'll take my 0.058 I naught, multiply it by cosine squared of 20 degrees, and that will give me, relative to the original sunlight, the intensity, right? And it's obviously be a small amount. So it doesn't look like it. There we go. Okay, so cosine squared of 20 degrees. All right, and so then we don't lose as much. We just lose a little bit more energy, and so then we end up with 0.052, the original intensity. Okay, and that's because having polarizers that are only 20 degrees apart, that's not losing much, right? Because if you have two polarizers that are 0 degrees apart, then there's no loss of energy. It might as well just be a single polarizer. And if they just have some small deviation, like 20 degrees, then it's not a big effect, not a big loss in intensity, because you're not realigning the light that much. Okay, so here's a question for you. What if we didn't have the middle polarizer? If we didn't have the middle polarizer, then the intensity passing through would be 0. So note, without the middle polarizer, the final intensity would be 0. So that's always kind of a neat trick, because you can get two polarizers that are perpendicular to each other, these axis-based absorptive polarizers, and hold one on top of the other, and the effect will be just total darkness. It's like a black sheet blocking out all the light. But then if you put a third polarizer between them, that is, for example, angled at 70 degrees, then all of a sudden you can actually, now it becomes transparent, right? So it's like you're suddenly turning an opaque material into a transparent material by sliding something else between it, right? Seems kind of counterintuitive. But of course we see why, right? Because otherwise there's no component, right? There won't be any component that this polarizer allows to pass through that is left over. But if we have something else in the middle, then there is a component that always is non-zero, right? Neat effect. Okay, so I'll leave example 2 for practice, and let's take a look at example 3. This is sunlight polarizing, and this is, this is the last one that I'll do. Right? I just figured I'd do one of them, and I'll leave the rest for your further practice. So sunlight reflects off a large sheet of glass with a index of refraction of 1.51. At what angle of incidence is the reflected light completely polarized? And what is the angle transmitted light makes with the surface in this case? All right? So I'll go ahead and draw a picture. So let's have this be our glass. All right. And so we're going to be going from air, all right, to our glass. So we have an NA of 1 and an NB of 1.51, okay? And we should assume it's air because it doesn't say otherwise, okay? And sunlight would be coming through the air. And then let's set it up, okay? So then our angle, or our formula, is just going to give us that tangent of theta p is then going to equal NB over NA, which is just going to be NB because NA is 1 here, okay? And so then we want that light to come in, so this will be our incident ray, like so. So I'll have it come in, and then get refracted, so bent down a little bit, like that, and then reflect at the same angle. There we go, all right. And then we need this to be our theta p, okay. So what angle of incidence is it? Okay, is the light completely polarized? Okay, so that would just be solving for theta p. So it's simple as that. Right? And again, that's just based on the idea that we need this to be 90 degrees, right? Even though it may not look like 90 degrees the way I drew it, but it's supposed to be. Okay? And so that's just going to be tangent inverse of 1.51. Okay, so let's see what that gives us. So tangent inverse of 1.51 gives me 56.5 degrees. Okay, so working at 3 figs. So 56.5 degrees, right? So that's the answer to part A. So that's the necessary angle, right? So any angle that is less than that, so more towards the normal, wouldn't have light that is reflected in an entirely polarized way, and any angle that's bigger, so light that's coming in at a really low angle, right? So really far away from the normal direction, would be not entirely polarized either. But if you got that sweet spot, if it comes in exactly at 56.5 for this particular material coming from air, well, there you go. You get full polarization. All right, and then the question then follows up and says, okay, well, what's the refracted, right? What's the transmitted? This transmitted would be the refracted. And so for that we can just use Snell's law. All right, and so then I'm just going to find this angle that corresponds. Okay, so I'll label that as just theta 2. Okay, that's this angle here. So let's call it theta 2. All right, so then using Snell's law, we've got N1 or NA sine theta p, which we found in part A, equals NB sine of theta 2. Okay, and so then we just want to solve for theta 2. So then theta 2 is just going to be 1 over NB times sine of theta p, all inside an inverse sine. Let's try to make space for it. There we go. So, oops. So sine inverse of that. All right, and that's just going to be sine inverse of 1 over 1.51 times sine of 56.5 degrees. All right. that is. So that's going to be sine inverse 1 divided by 1.51 times sine of 56.5, no rounding here, 33.5 degrees. Okay. And if you take those two angles, they should add up to 90. Do you see it? Okay. Because that was the condition for full polarization. So note that theta p plus theta 2 has to equal 90 degrees. All right? Because the idea is that this has to be 90, and if that's 90, then these two angles have to make 90 as well, right? Because it's 180 altogether. Kind of neat, huh? So we could have literally just, I could have even avoided using Snell's law and just took 90 minus that, and that could have given me part B. So it's a good way to check your work, I suppose. Okay? All right, so that is polarization, the three types. Thank you.